Algebra 2 students, this will be a video that at least one of you is really going to love. So when it comes to what we've been talking about, exponential functions, f of x equals b to the x, and then the transformations of that, f of x equals a times b to the x plus h minus k, or plus k. This is a minus, sorry. X minus h plus k. And then we talked about how do you compound interest. Some function of time t equals p times 1 plus r over n to the nt. That's compound interest. And then we have continuous interest, which is this e to the rt. All of these functions are talking about y values that are powers, or something raised to a power, a base raised to a power. Short history lesson around 1600 ACE, a man named John Napier invented a way of doing complex multiplication and complex division and complex raising to a powers much easier. So he changed multiplication into addition, and he changed division into subtraction, and he changed raising a number to a power to multiplication. Now the way he did that was he created something called a logarithm. Logarithm. And logarithms were pretty incredible for navigation, and really played a huge part in the age of exploration when the Western European powers started to travel the globe and colonize the other parts of North America, Africa, India, Asia, really kind of expand that Western influence for better or for worse. Logarithms made that possible. Now, fast forward a couple years, and Euler, my favorite mathematician of all time, the guy who comes up with the number e, discovers that logarithms actually have another use. And that other use is actually how we start teaching logarithms today. And what Euler noticed was that you could use a logarithm to rewrite an exponential equation. So let's clear the screen here. Here's what Euler figured out. That if you take a number b and you raise it to some unknown power, call that power smiley face, then you get some number, let's call it star. And Euler was able to show that logarithms allowed you to rewrite this exponential equation as a logarithmic equation. And Euler said, well, the way this works is it's going to be log base b of star will equal smiley face. Now, I use smiley face and star instead of x and y because as we use this in x and y variables, sometimes it can get confusing for students. So this right here is the definition of a logarithm. It allows you to change forms. We have two forms. We have exponential form, and now we have logarithmic form. And some of the work you're going to do tomorrow is just changing form from exponential to log and from log back to exponential. Let's try an example of that. If I told you that 3 to the 4th equals 81, write that in logarithmic form. If I told you log base 7 of 343 equals 3, write that in exponential form. Pause the video and give that a try. Based on the definition, if b to a power equals, if b to the smiley face equals star, then log base b of star equals smiley face. So here, log base 3 of 81 is equal to 4. These two equations say the exact same thing, they're just different forms. Over here, If log base 7 of 343 equals 3, then that means 7 to the third equals 343. Practice saying that right now as you're watching the video. Log base 3 of 81. Log base 7 of 343. You are required in a math class to not only know how to write and communicate your mathematics by writing, but also by speaking. So a lot of changes or a lot of changing forms. Another thing that we do sometimes is we change forms while we have variables in there. So you might see something like 3 to the x equals 7. Well, then that means log base 3 of 7 equals x. You might have something like log base 5 of y equals, 10. So that means 5 to the 10 is equal to y. So you got to be able to deal with variables as well. Logs have some interesting properties that we can prove by taking some equations that we know are true. Let's do something very specific. What is 2 to the 0 power? What is 2 to the second power? What is 2 to the negative 1 power? Well, hopefully you know 2 to the 0 is 1, 2 to the second is 4, 2 to the negative 1 is 1/2. And then writing these in logarithmic form, that means log base 2 of 1 is 0. Over here, log base 2 of 4 is equal to 2. And log base 2 of 1/2 is equal to negative 1. So a lot of students at this point are starting to realize what log is saying. Log is saying, what power do I raise the base to get this number? If I raise 2 to the negative 1 power, I get 1/2. If I raise 2 to the second power, I get 4. If I raise 2 to the 0 power, I get 1. Now, if we go less specific and we then look at some more general ways of writing those equations, we might say something like b to the 0 equals 1. B to the 1 is equal to b. B to the second is equal to b squared. B to the negative 1 is equal to 1 over b. And now if we change all four of those, log base b of 1 equals 0. It doesn't matter what the base is. To get any number to equal 1 by raising it to a power, you'd have to raise it to the 0 power. Log base b of b is equal to 1. If I want to get the base, I just raise it to the first power. Log base b of 1 over b is equal to negative 1. And I saved this one for last because it looks a little tricky. If you use this side here as the exponential side and you use this whole thing as star, log base b of b squared equals 2. And that should be pretty obvious. What power do you have to raise b to get b squared? You got to raise it to the second power. These are true for all bases, no matter what. No matter what the base is, log base b of 1 is always 0. Log base b of b is 1. Log base b of 1 over b is negative 1. Another interesting point to look at, and we'll change slides here. Another interesting thing to look at is this idea that we talked about with b to the x equals y. When we look at that exponential function, and let's just say b is bigger than 1, but if it wasn't, it would just look like this. This function had a domain of all reals, and it had a range of y is greater than 0. What I stressed about the range and the fact that this function was 1 to 1, but what I stressed about the range is that there is no way to raise b to a power to get a negative number. So when we switch forms and we're now talking about log base b of something, call that something star, and then that equals some unknown thing, call it smiley face. If I try to take log base b of a negative number, what I'm asking is, what power could I raise this base to get a negative number? And the answer is No solution. Not possible. Not in the domain. You can't actually take the log of a negative number. There is no power to raise a positive base to that would give you a negative number. There's no value x here that gives you a negative y value. That's just not possible. So you can't take the log of a negative number. You actually can't even take the log of 0 because there's no way that this thing will ever equal 0. So you have to take this star here, has to be a positive number. Can't be anything else. Good? So Euler was the one who gave us this definition that log base b of something is equivalent to b to a power equals that thing. Euler was the one who showed log base b of star equals smiley face. That means that b to the smiley face equals star. Now, a couple logs that we use all the time. They're so common that we actually don't write the base. Kind of like how we take the square root so much we quit writing the 2 there. Technically there's a 2, but we don't write it because we write square roots all the time. If we take a cube root, we write the 3, right? If we take a fourth root, we write the 4. But with square roots, we don't have to write this. And as a matter of fact, you're kind of told not to write it. Well, with logs, there's 2 bases that we use all the time. And one is base 10. It's called the common log. So when you see log of 4, what that means is log base 10 of 4. So if I told you log of 4 equals x, then that means 10 to the x equals 4. This is what log of 4 means down here, but we never write it this way. Another one we see is called the natural log. Now you might be saying, wait, natural log, ln, why did you put the n second if it's natural log? Well, remember, a lot of European countries have languages where the adjectives come after the noun. So instead of calling it natural log like we do in America or in English, a lot of French and Spanish and European speakers, Latin speakers, would say log natural, logarithm natural, so ln. And ln of 4 equals x. ln is log base e of 4. So when you see ln of 4 equals x, that means e to the x equals 4. You'll notice, if you have your calculator handy, that log and ln are buttons on your calculator. There is a way to get a different base than 10 or e, but I'm not going to tell you how to do that because it's going to cheat you out of some interesting math that I want you to know. But for now, you just need to know that you can use the log button on your calculator and the natural log button on your calculator if you need logarithms. So tomorrow, your homework or your classwork is all changing forms, exponentials to logs, logs to exponentials, and playing with this definition. If you do one thing only tonight from watching this video, know this definition, that log base b of star equals smiley face is the exact same thing as b to the smiley face equals star. That's all I got for you today. Peace.